In today's lab, we are going to implement the simple and Gerhardt cellular automata to study the behavior of the spiral wave with different parameters. Like last week's, I have provided you with two Java programs. The first code implements excitable media using the simple three-state cellular automata. As you can see here, we can download the code from the Moodle site. In this code, this is simple three-state ca.java, and in this code, as we can see here, the first loop initializes the cell. Apart from the cells in the last row, which are in the excited state, the other cells are initialized to their resting state. So the last row, all the cells in the last row are in the excited state, and the rest are in the resting state. The next generations of the automaton are calculated in this while loop. So this while loop using the rules we have studied in the lecture, calculate the next state of the cells and calculate the next generation of the grid. This piece of code here breaks the wave in its half wave to initiate a spiral wave. You can generate a plane wave by commenting out this piece of code. So comment out this piece of code and run the code to see the output, and in the next run, please uncomment this piece of code to see a spiral wave. The rest of this while loop updates the states based on the rules presented in the lecture. So as you can see here, this piece of code, find the excited neighbors and then update the state. So in the first part of the lab, please perform what you are asked in the lab script. In the second part of today's lab, we will experiment with the Gerhardt cellular automata to simulate how waves propagate in heart tissue. You can download the Gerhardt model implementation from Moodle. Similar to the simple model, in this implementation, after initialization, the wave is split in two. So here we have initialization, and here the wave is split in two. You can reproduce a plane wave or a spiral wave by commenting and uncommenting this block of code. Unlike the simple cellular automata in the Gerhardt model, we have several parameters, as you can see here. You can find the description for each parameter in front of it. So for instance, here, V max is the maximum possible value for V, or EXCI is a constant uh, determining the cap or the maximum value for V. When V is less than this V excited, we can make a cell excited. So V excited is the cap for V value. And if we want to make a cell excited, its V value should be less than this V EXCI. This is a constant. So we have lots of parameters here, and the description of each parameter is in front of it. For instance, a cell can be excited if its V value is less than the constant value V EXCI, and at least K0 EXCI neighbors of this cell are in the excited state. So we have two constant for excited cells, or to make a cell excited, and we have two constant values to make a cell recovered. And by the way, we can see here G up and G down positive numbers. So if you remember, we can control the transition speed between states using these two variables. In the lab, please experiment with changing these parameters to see the effects of each change. In the end, here, we have one exercise. In this exercise, we will modify the code for the simple three-state model, this code. To develop four-state cellular automaton. In this implementation, each cell should have two variables, state and time to state change. The state variable represents the current state of the cell. The current state of the cell is determined by this state variable. The second variable is time to state change. Using this variable, we will control the number of steps that should pass before the cell's state changes to the next one. So if you remember, in the simple model, we cannot control the transition speed. With this modification, we want to make this simple code controllable in terms of transition speed. So we want to modify this simple code somehow that the transition speed is controlled using this time to state change variable. So you can find some hints and descriptions here in the lab manuscript.